All right. So we'll begin with an Our Father. In the name of the Father, Son, and Holy Spirit. Our Father, who art in heaven, hallowed be thy name. Thy kingdom come, thy will be done on earth as it is in heaven. Give us this day our daily bread, and forgive us our trespasses, as we forgive those who trespass against us. And lead us not into temptation, but deliver us from evil. Amen. You guys were supposed to join me.
Oh, sorry, man.
What's that? All right. You up for a mustard seed first, too?
No.
Have
Yeah.
you been reading my mustard seeds?
No.
I don't make them up. They come from my book. Today's is really long.
I thought you
So
made
I'm
them
going
up.
to read it really quick. Listen carefully. Pay attention. This one actually was pretty good. We have built into us a desire to be like God, and yet we cannot be God. It is the friction caused by these two facts that leads us into sin. We want to be like God. Very often we choose the apparent good and eat the fruit, believing that this will lead us to independence and to become more like God. Very often we choose the apparent God, believing that such is a valid response to the desire within us to be like God. It is not. We cross the line of valid response to the desire to be like God when we forget, conveniently or otherwise, that we are dependent and always will be dependent on God for our existence. When we seek independence from God, we seek and find catastrophe, disaster, darkness, useless suffering, despair, and anxiety. For us to be independent of God is impossible, yet we continue to seek it. The first sign is always disobedience or infidelity to the word of God. Anyway, one nice thing out of this is I think people's faith might be, it could be shaken or it could be brought stronger. I don't know. I hate that I can't go to church. I'm really, to not be able to go to Mass on Easter Sunday, that's going to be crazy.
Oh, it's on TV, man.
I know you can do it on TV, but it's just not the same.
I forgot that, like, even Easter Sunday you can't go.
Yeah, it's going to be, it's just not the same. I mean, to me, going to church is all about the community and seeing people and, you know, being all together. But But we will continue, we'll persevere, and we'll get through. All right, so what I would like to do today, so you guys did really well on those problems last time, but as I saw on Friday, it was evident that there was a lot of guessing maybe going on, maybe uncertainty in how do I do these calculations. So as boring as it might be, what I would like to do is work through the problem of the challenge on Friday. Just I'll put that up, and then I just have another problem that I'd like to work through so that you can, you know, see the process of as we go through these. So these problems are not very difficult. It just requires some geometry. Number one, recalling what is volume of different shapes and so on, and recognizing what are you talking about. So what I really like about these buoyancy problems is it requires you to really pay attention to what do I know and what do I want to know. Those first two steps in problem solving, which I've been stressing all year of, do I, you know, drawing a picture, and what do I know and what do I want to know. Then the actual math involved in these problems is pretty easy, but it all comes back to F equals ma, as always. So that I said at the beginning when we started Newton's laws that F equals ma is probably the most important equation in physics. All right, so let me run through what we did on Friday, because I didn't want to hold you too long Friday after we did our challenge of putting the pennies in the mass in the jar. But let me go through those calculations. I did post the solution, but you didn't get it because Blackboard is down, so nobody saw it, right? All right, so if you have any work out, I asked you to submit that to me, but all right, and give me a, you know, stop me if you can't see this board well enough.
Can't see it well enough.
All right, let me move out of the way first.
Good.
It's like blurry.
Good, Drew.
Okay, hold on a second.
Drew.
Yeah, Drew, we hadn't heard from for a long time.
Yeah, where you been, bro?
Now we can't see.
I was enjoying my summer until Mr. Busman sent that email.
You were enjoying your summer?
Enjoying.
What are you thinking, Drew?
Just Benedictine, we have school.
Well, here's my plug. Let's see. I can't figure out how do I get to.
Coach, you think I have time to go upstairs and make waffles?
No.
I'm hungry.
Just
All
bring
right.
us with you.
So boys, I'm going to mute you all just so like extra noises doesn't change the video. So one thing. And second, now I know you guys are all exhausted and you're like, oh, we have school. So I'm just going to jump in on those couple of comments. We are like, this is unprecedented what we're experiencing here. And quite honestly, this is when intelligence is what's going to get us out of this. So I just want to reiterate the importance of that, the importance of knowledge, the importance of creative thinking of new ideas. Like this is major. This is people's lifestyles. This is the economy, the businesses. You've never seen anything like this, nor I hope you never do again in your life. But the only thing that's going to get us out of this is intelligence. And so this is an opportunity for you to grow in your mind and how you think and all of those kinds of things. So, we need that right now. So that's my plug. And I'm excited that Benedictine is really valuing education this much. So we'll put it that way. All right, so this time.
If the Chinese people would stop eating bats, then we wouldn't have this problem.
Exactly. That's what I'm
Well,
saying.
From a bat.
whatever it is, that's
We
what
just
we have
need
to
to-
figure out, right? So again, it comes back to the intelligence.
We just need to talk to Reese.
Okay, I'm going to mute. I'm going to hit mute all. So don't take any offense to that. It is just for more control and being able to pay attention in the class. If you have a question, you can use the symbol of raising your hand, or you can just wave to me and I'll stop and unmute you. But if you have questions, I don't like this because I do like the interaction. I think maybe you guys would be fine. Okay, there we go. Okay. So let's see. Okay. So are you just seeing me on your screen? So you can go to speaker view. If you go to speaker view, you should only see me. But I'm going to go into gallery view so that if you have a question, just raise your hand. All right. So Drew, if you can't see this very well, let's see, that's the best we're going to do right now. All right. So we're going to go back to this question here. Okay. The question on Friday was how much mass was going to be necessary? So we had a balloon and we had the mass hanging, right? So what I said on Friday, the key to that was you had to look at this as a whole system. So you had to look at this as one object, right? So if I put my boundary around the whole thing, the forces that were on this object would be weight and your buoyant force acting up. So because you wanted it to float, you need that buoyant force to equal the weight, right? So that was the key. The ultimate question was, how much mass did we need to put inside the jar to make that whole balloon submerge? Okay, so when we did that and we put them all underneath there and they all submerged, what we needed to figure out is then what is the buoyant force? So what we know is the buoyant force, if we replace mg for our weight, then we want to know what is this buoyant force. So this is equal to the weight of the water displaced, right? So if we come over here, the weight of the water displaced, our buoyant force would be equal to rho times the volume times g, right? So this volume that we need right here would be our total volume. Okay. And that total volume displaced would be the volume of the balloon plus the volume of the jar, right? So those two things together. So in order to do this, you needed the volume of the balloon 4/3 pi r cubed, which is the volume of a sphere. And then you needed to add to that the volume of the jar, which is a cylinder, pi r squared times h. So if we plug in our values for that, I got the total volume And make sure you're using the radius. So I guess I can plug that all in. 4/3 pi r. The r of the balloon was 0.0381 meters cubed plus pi times 0.03 meters squared times 0.07. Okay, so that was the volume. This would be the entire volume that we're going to displace. And I got that total volume to be 4.293 times 10 to the minus 4 meters cubed. Just give you time to write that down. All right, everybody, when I'm done with this, we're going to go through another problem that I'm going to pull up. All right, so with this volume, that becomes the volume of water displaced when I put this entire thing in the water, right? So it doesn't matter, it does matter its shape in terms of the volume, but if the whole thing is submerged, the total volume of my object is what's going to be causing the buoyant force. So when I come over here, erase this, our buoyant force is going to be rho times V times G equal to M times G. So our buoyant force is the density of water times the volume of water displaced times G. That equals our mass times G, which is the weight of our object. So the G actually cancels from both sides. So all you need on this side is the mass that's going to be displaced is going to be the density of water, which is 1,000 kilograms per meter cubed, times the volume. So the key to this problem was understanding that the volume would be the total volume of the balloon and the jar. So what I understand, most of you guys did not have the jar involved in that. So that's 4.293 times 10 to the minus 4 meters cubed equals the mass that would be displaced, your total mass. And let's see, for that I get 0.4293 equals mass, kilograms. Which is 429.3 grams. So that would be the mass of the jar and the mass in the jar.
Is it
Okay.
any?
Good
So-
it feels to have leadership next block.
No, you don't have your leadership or music or art.
That's what I'm saying.
Oh, I don't have band.
I don't
Ah,
have a class, and then I have lunch. So I basically have like an hour and 50-minute break.
So you know what you're gonna do? Your physics homework.
thanks.
Play
All right,
2K.
so what we're gonna do now, gentlemen, is I'm gonna pull up a problem. So I'm gonna do a screen share that I wanna work through this problem together. Let's see if it'll,
All right, let's be honest. Who's been doing the poetry work?
Are we?
Do we have a thing for that class tomorrow?
Yeah, man. It's a class. It's a real class.
It's an English class. 10 minutes
Right.
of free write?
Hey,
all
I'm
right,
there.
maybe it did work well when you guys were all not videoing anyway. All right. So what we're going to do is I'm going to give you time to look at this problem. We're going to work through this together. You took that as advice to now let me, oh, you all muted yourself. Very good. All right. So as we take a look at this problem, all right. So I'm going to give you 2 problems like this for homework that are not due till Wednesday. I will also post the solutions, and you know what I mean when I say I post the solutions. They are not just to get it done. They're so while you're working on it, you can check your work. So you can, you know, as you're working through it, check through what we are doing. So on this problem, a large rectangular raft is not completely submerged. So the whole height of this, we don't know what it is. It has a density of 650 kilograms per meter cubed, which means it's less dense than water. So it can float in water, right? But it's going to have to displace a certain amount of water in order to float. The surface area on the top of the raft is 8.2 meters squared. That should be squared, and its volume is 1.8 meters cubed. So notice it's not that the area is more than the volume. This is units of meters cubed, and this is meters squared. The density of the lake water is fresh water, so it's the same as our water of 1,000 kilograms per meter cubed. The first question is calculate the height of the portion of the raft that is above the surrounding water. Okay, so how would we go about doing that? So the first thing is, let's draw a picture and label what information can we figure out here, and what information do we know. So in this spot, and again, maybe that's not enough room to solve your problem, but you already have the picture there. We need to give a label to this distance, the entire distance right here, right? Because I can determine that by the volume. So what I can determine is this total height X. What's in shaded here is what's inside the water causing the buoyant force, right? All right. So what might that picture look like? So let's see how this works here. Let me go back over here. I switch to, I just want to make sure you can see, I guess with the screen share. All right, does everybody have that? If I stop the screen share, then it'll put my whiteboard up better. So everybody draw themselves a quick picture of that diagram. And before I take off my screen share, and that way you have that looked at. Okay. Give me a thumbs up. Are you good with the diagram? Everybody got it?
No.
Oh, no, I didn't get it.
All right, well, I'm going to redraw it on my whiteboard then. All right, so basically you have a raft that's rectangular, right?
Tricky.
When you put it in the water, only so much of it submerges inside the water. That's this, right? The question is, how much is out of the water? So we want to know this height, H. How much is out of the water? So what we were given is the volume, right? So what we do know here is the density of the block is 650 kilograms per meter cubed. We're told the area is 8.2 meters squared, and the volume is 1.8 meters cubed. So if I know the area and I know the volume, that will allow me to calculate this total height right here. Understanding that it's floating in water will allow me to figure out how much of the raft went inside the water. So if I can figure out how much went in the water, then I can figure out the H, how much is sticking out of the water. So you had that with your boat. When you built the aluminum foil boat and you put your pennies in, as it slowly went down, right? Only so much of it submerged and some of it stuck out. So what we might want to know here is when you put that in and we had 10 pennies in it, how much of it was down inside the water, how much stuck up out of the water. All right, so area, volume, from that, right? The volume of anything is the area times, I don't want to use the same letter.
Does that say 82 meters squared or
8.2.
Okay, and then for V, that says 18.
It's 1.8.
Oh, okay.
Smart.
Wow, Matt, it's you.
Let's see. Okay, good. Any other questions? So this means our volume. I'm going to call this height here X. That's going to be the total height of that side. I don't want to use H because H is the letter of what we're looking for, which is what's sticking out of the water. So I'm just going to call that X, right? Since I know these two values, I can solve for X, which would be volume divided by the area, is going to be the actual height of the rectangle. How big is it actually going to be? All right. So if we plug in our numbers there, you would have 1.8 meters cubed divided by 8.2 meters squared to give you X. So that height would be, I get 0.22 meters to the X. Okay. So again, that's the total height. We'll call that X. Then the water covers it up, right? This, what is left over, this little bit is what we're going to call H. So the whole thing is, let me write that on this other side. That's going to be H. X is the entire height. H is what's sticking out. So the ultimate question is, what is that H, right? So the process now is to find out, what is this? How much is sticking in the water? So what I wanted to do this problem to hold you accountable to what are we actually saying in this buoyancy equation. Okay, so everybody, what would be the free body diagram, the force diagram on the raft as it sits and floats in the water? So as it sits and floats in the water, all right, CJ, what forces would be acting on that raft?
FB,
Okay, buoyant force, which way would that act?
down. No, it'd be going up.
Up, which one?
Up.
Up. All right, so the buoyant force is what pushes it up out of the water, right? So there's a buoyant force. Is there a weight?
Are you still asking me?
Yep, CJ.
Oh, yeah, there is.
Okay, so we have weight. There's no normal force, no friction, no air resistance, no tension. A couple of the problems I give you later, they're going to have a tension like somebody's lifting something out of the water. That would be it, right? We see that equation all the time. Since we know there is no acceleration in the y, then we know our summation of forces in the y equals 0. So our force buoyant minus weight equals 0, and your buoyant force equals weight, right? So that's what we've been looking at in all of our problems so far. So the beginning of this, I just did a little geometry, okay? Can I find the weight of the raft? Ben, what do you
Yes.
think?
Yes.
Yes, I can find the weight of the raft. Brendan, How would I find the weight of the raft?
Using that right there.
Using math? Is that what you said? That's true. All right, now, if I could find the buoyant force, but I can't get the buoyant force, let's maybe start there. Somebody write me an equation or tell me what an equation would look like for the buoyant force. So we're going to separate this. The buoyant force is equal to,
So if you find the buoyant force and you find the weight, right?
we know that they're equal, correct. What we don't know is what is this, how much is the raft in the water, right?
How do you find that out?
So if this is X and this is H, how much is this?
X minus H.
There you go. So this height would be X minus H. Everybody good with that?
Yes, ma'am.
Okay. So in our buoyant force equation, it's the density of water times the volume of water displaced times G, right? So that's our equation for buoyant force. The density of the fluid, it doesn't always have to be water, the volume of the fluid displaced times G. Remember, we get this as a result of that's actually mass. Density times volume would be the mass times G. So we know the density of the water, I didn't write that down, is 1,000 kilograms per meter cubed. The volume of water displaced. Before I do it, see if you can write me an equation for the volume of water displaced by the raft, which is going to be just this. How much of volume would I put in there? What would be my equation for volume?
Y equals mx plus b.
No, that's the
Great,
equation of
Ben.
a straight line. How about Brendan, you know the volume?
Looking at it right now.
So we go back to the beginning. The volume of the entire raft was A times its total height, right? What would be
So
the volume of the raft that's inside the water?
It would be A times X minus H in parentheses.
Correct. So we haven't changed the area. So when you guys built your boat, some of you said changing that area, but actually you were changing the whole volume of what you were able to displace in your aluminum foil boat. So how much volume goes into the water would be the area times the height of what goes into the water, which we discovered the height to be X minus H. So this volume would be A times X minus H. And that's written pretty small. I don't know if you guys can all see that. Write that over this way. Thumbs up if you're following along. Matthew, did we lose? Oh, there he is. Okay. Okay. So what we're really looking for, do I know this and I know that, right? So I know the density of the water, I know the area, I know X, I just calculated that. I'm looking for H and I know G. So what I don't know, so I can get everything over here, is I need something on the left side. So that's the equation for the buoyant force. But I don't have a number over here, so I actually have two unknowns, my H and my buoyant force. So I have to go back over here to say, well, my buoyant force was equal to the weight of the raft. How much does the raft actually weigh? If I have the density of the raft, which is 650 kilograms per meter cubed, its actually weight would simply be its mass times G, right? So the weight of the raft is still going to be mg. But the mass of the raft, no different than up here, the mass of something is its density times its full volume. For the mass of the raft, it's just going to be the density of the raft, right? Times its volume, the full big volume, because the whole thing is in the water, times G. All right, thumbs up if that makes sense.
You're doing great, Coach.
Oh, thank you. You're looking for the A plus for the fourth quarter, huh? You
Yep.
can do it on your own, CJ. You always, all right. So now I have two equations with, I can do this, right? I have all these numbers. I know the total volume of the raft. I know its density, and I know G. So now what I'm going to do is go back to say those two equal each other. And instead, I'm going to put these two equations equal to each other and solve for my H. So I'll write that over here. I'm going to kind of get rid of this information that we know, I'm out of room. But I'm going to let you do it. Hopefully you have your calculators out. So don't watch me do it. I'm going to set it up. I'm going to pause and let you solve for H. Looks like Brock's wanting to join us here. All right.
For the last 10
Getting
minutes.
more board space. You guys solve for H.
Rock. Rock.
Hey, Brock.
All right. Good morning, Brock. I think my laptop's going to fall off my table. All right, when we put it all together, this is your equation. Looks complicated, but hopefully it all makes sense. Your G will cancel out on both sides. We don't have G. The most important here is to be careful which densities you are using. Is it the density of the water or the density of the raft? Okay, so make sure you're putting in the right densities. You can certainly plug in your numbers and solve for everything. I like to do the math and get the H by itself, right? So what I'm going to do is, this is all being multiplied together. So I'm going to get rid of, divide by the density. So you have A times X minus H equals density of the raft times its volume divided by density of water, right? Divide the A over. So I'm going to keep solving it, but my preference is that you're working it out on your own paper as I continue, and then let's see if we get the same answer. So it's some messy algebra.
Good, you got 5 minutes.
Thank you, thank you. CJ, you having anybody over for lunch? What are you making?
No.
No.
It's breakfast.
What
Breakfast.
you can make me some pierogies though.
I know, I do need to have some for y'all. I'm hopeful that maybe we'll be able to have like a graduation party. Wouldn't that be nice if we can end all this?
Ma'am, I won't be at a graduation party.
We all got a Bushman's house.
With his bees.
We need it to go down. All right, gentlemen, that was a lot of algebra. Right? Any questions? How'd we do on it?
Amazing.
It's good.
Good. Thumbs up. Brandon. Does that make a little bit more? Now, there is a little bit more to the problem. So let's see. You know I'm going to make the most use of all my time.
Before we get kicked off.
Screen share again here. Let's see. Okay.
Is that 0.077 at the bottom?
0.077, yes. Okay, I'm back to the screen share for you.
So we have 2 problems, I guess, for homework.
Yes. Okay, now it says calculate the magnitude of the buoyant force on the raft and state its direction. So all we would do is go back and actually put in that height, right? So we'd go back over here and put in the height and actually find the actual buoyant force. And then this last one, if the average mass of the person is 75 kilograms, calculate the maximum number of people that can be held on the raft without the top of the raft sinking. So of course, we would do the maximum buoyant force then, right? So in that case, we would go back over here, and instead of x minus h, we'd actually use the full volume of the raft. So the most that the buoyant force can be on the raft is if the whole thing is submerged. So we would find that maximum number and say you'd have slightly less than that number of people on it, right? So what I would do is I'm going to share with you the solution to the rest of this problem. We're going to run out of time. So I will share that solution with you. Work through that problem. My suggestion would be that you would work through the problem all by yourself again, checking all that work, and then do the 2 problems that I will assign for homework. And then those 2 problems will be due on Wednesday.
How do we see the problems?
Actually, you guys want to come back on video? Let me see your faces again real quick.
Yeah.
There we go. All right. I'm going to email them to you with an attachment because it doesn't seem like the document, the shared documents on the Blackboard is working. And I'm going to assume that it's not going to work today. So look for an email from me that has these as an attachment. Okay?
All right.
Anything y'all need help with? Did that help clarify some things?
Are the answers going to be there too?
That's my goal, yeah, because I want to be efficient with the understanding that, again, it's not about getting the answers, it's about working through the problem and solving it, right? So definitely I will provide you, maybe I'll provide you solutions for one of them, and then your homework is to scan your solution to the second one and turn that in.
How do we scan them?
Yeah, I don't know how to do that.
Picture of it, you can take a picture of it, or
I can do that.
if you have a printer, all printers can be scanners.
What if Blackboard's still down?
My guess is it will be. That's why I'll communicate through email.
Okay.
Once I figure out that it's okay, we can go back to using Blackboard. But I like this better. I think this is going to go much, much better.
Wait, you said email it to you?
Say that again?
You said email it to you?
Yes, Phil Howard.
Homework?
If Blackboard is still down, my preference is that it's in Blackboard, that you still have Blackboard working and that you can just submit it on Blackboard. But if that's not the case, then we'll do it as an email. Okay? Lunchtime. Did we lose
Mandatory
Brock?
lunchtime at my house.
So next time.
Brock didn't even stay for 1 minute?
Yeah, he's gone.
He's gone already.
He said he had to get his participation.
Nah, I'm not. You know me. It's not about participating. It's about learning. So I hope that you learned a little bit today, and I hope that it clarified any of your questions that you were having with buoyancy force. It actually, I hope, number one, you're getting more and more comfortable with problems that look like this, that may appear to be complicated, but if you break it down into steps, it's not too bad. It actually makes a lot of sense. So the goal of the year has always been thinking and your problem solving skills. And how do you solve stuff you've never seen before? So anyway, Brendan, you gonna smile for me today?
What time is lunch supposed to be at?
Right now,
Oh,
10:50. It's lunchtime. I held you by 1 minute. All right, gentlemen. I'll see you Wednesday.
When's the
Have a
next
great
class
couple
start?
days.
12.
bro.
Theology.
This, God, Bossman.
You have time to even go take a walk.
Who eats lunch at 10:50?
Right?
It's 11. You don't have to eat now. You can wait till 11:30.
I'm
No,
waiting
like,
until 12 when my next class is.
Your next class should be at 11.
12.
12, right. 12 to 12:50. Yes.
Thinks I have a class next block.
No, you're hype.
So
I am
Ben,
hyped.
I'm going to
I'm
right now try to get this email to you all so you can make use of this time.
yeah.
Oh,
Use of this time and play Madden. That's what I'm gonna do.
Oh.
Oh, you stuck.
No, there's some strategy in that. The game plays and stuff. Matthew, you doing all right?
I'm great.
Did you get my email about the boat and stuff? You good to go?
I did. I'm gonna do that today.
All right.
Matt hair.
And Drew left us already, but he cheated. He must have used like a whole roll of aluminum foil. He had a neat design. He made coils, 2 coils with the, and he put the pennies inside the coils like it was like a tube, and the pennies hung down inside. It was unique, but he used more foil than he was allowed.
Peter.
So he did have a few more pennies. But Matthew, the number to beat is 27 pennies and 2 nickels, right, Frankie?
I think so.
If you can prove to me you beat that, then you can be the winner.
Thanks.
And then I might have another challenge for you on Wednesday. Let's see. Oh, Brendan, you'd rather do these problems?
Yes.
Yeah.
Really? Okay.
Yes.
Yeah,
No.
these are better.
Because it's just like finding all the materials you have to need for like
A
5
piece
minutes.
of aluminum. No, this one I'm going to demonstrate for you. This one's going to be good. Well, maybe.
Like
I
the
don't
one
know.
on the balloon one, that was kind of pushing it.
Which one?
Balloon and the jar and all that stuff.
Oh, you didn't have to do it. You just had to do the calculations for it. Which did you do? Because Blackboard's down. I didn't see everybody's. I saw some people. I did see some people had the summation of forces. I looked at a couple real quick before it all went down, but I didn't get to grade everybody's. So. No, our next, after we finish with buoyancy force, the big question is how are we testing you guys and grading you guys? So
No test.
my thought is I'm going to have you work out a problem, and then on 3, I'm going to have you hold up your answer to your camera. And then later I will go watch the video and I'll grade you all on your answers.
Let's not do that.
Thanks.
That's the most secure way I think I'm going to be able to grade you.
You can send us like a link, an online link, and you can make a quiz there.
Yeah, that's what a lot of people are doing. But
We promise we won't use our phones.
Using your cell phones, calling a friend, or
We promise we
We
won't.
can't learn as well when we're writing.
can't learn as well when you're writing.
Mm.
Oh,
If you're not cheating, you're not trying.
Amen.
that is a saying. That saying comes from a baseball player, doesn't it?
Yeah, Jose Altuve.
Yes, yeah. See, sometimes I know my stuff. I couldn't tell you his name because I'm not very good at names, but I knew it came from a baseball player. So, all right, boys. I'll send you this email. Our class is over. I do miss you all. I'm sorry that we can't be together in person, but this is not bad. This is the next best thing.
Allez.
But I'll see you on Wednesday.
Yeah.
Now, I will give you one piece of advice, having taught in the block scheduling for many, many years. Do today's homework today. And not, like, don't put it off till tomorrow because it's not due till Wednesday, because it's more meaningful for you today. And, you know, I definitely think you should take a break when you're done with all your classes and then come back to your homework. But it does work well if you, like, do your you know, this set of classes today, that set of classes tomorrow, and then you're ready. But whatever works for your schedule. So, all right, gentlemen, always a pleasure to teach you. I hope you learned something today. And we'll see you Wednesday.
So,
Take
Bye.
care.